Australia is the starting point of this voyage into space. Travel is supposed to broaden the mind. This journey is to measure the cosmos, to set our position in the broadest context of all, the universe. We begin in Australia because it's good for observing the nearest galaxies. Two mini-galaxies called the Magellanic Clouds. The small cloud is to the center, the large at the right. In the large cloud in 1987, a supernova blows. In fact, this supergiant expired 160,000 years ago. It's taken that long for the light of the flash to reach us. Andromeda is our closest major galaxy at over 2 million light-years. At 10 million light-years, the Silver Coin Galaxy, a spiral like Andromeda, and like our own galaxy, the Milky Way. We probably look like this. A spiral from above, the M83 galaxy, also at 10 million light-years. We're now at twice the distance. The light of this galaxy takes 20 million years to reach us. This one, 35 million years. And from the beautiful Sombrero Galaxy, 40 million years. Vast distances, but all these spirals are relatively close to us. This galaxy, Virgo A, is different. It's shaped like a basketball, an elliptical galaxy, one of a cluster up to 60 million light-years distant. The Virgo cluster is part of a supercluster of about 1,000 galaxies. Galaxies cluster because of mutual gravitational attraction. But how do we know this? How do we measure the cosmos or even the distance to our galactic center? Our galaxy is one of 30 in a local group. That group is part of a cluster, and the cluster part of a supercluster. Superclusters form strands across the universe. To help construct this model, astronomers use what they call standard candles. There's a standard candle in this galaxy, a pulsing star that brightens and fades as regular as clockwork. It's called a Cepheid variable, a star whose brightness varies as it expands and contracts. This one is big and bright and pulses slowly. But this Cepheid is smaller and dimmer and pulses faster. The speed of a Cepheid's pulse is directly related to its intrinsic brightness. So if we know the distance and true brightness of these nearby Cepheids, we can calculate the distance of remote Cepheids. Cepheids that appear fainter, but beat with the same pulse. In this way, we know that the Andromeda Galaxy lies at a distance of 2.2 million light-years. Cepheids in our own galaxy are compared to fainter Cepheids here in Andromeda. But ground-based telescopes detect Cepheids only out to 15 million light-years. It takes the Hubble Space Telescope to see them in this galaxy at 55 million light-years. And in this galaxy at 80 million light-years. Beyond that, another sort of standard candle is necessary. Astronomers call it a Type 1 supernova. It occurs in a two-star binary system. A white dwarf, a star at the end of its life, swirls at the center of an accretion disk. It draws material from its partner. When the dwarf reaches the mass of 1.5 times our Sun, it explodes, a Type 1 supernova. The flash intensity is always the same. It's our new standard candle. From Cepheids, we know the distance of this galaxy. But because it also has Type 1 supernovae, that gives us the distance to our new standard candle. That candle, a Type 1 supernova, lets us measure up to 100 times deeper into space. But our journey has barely begun. In the 1920s, the American astronomer Edwin Hubble discovers our expanding universe, galaxies traveling outward in all directions. The evidence is in their light. As a galaxy speeds away, the lines of its spectrum move increasingly toward the red. The farther and faster a galaxy recedes, the greater the shift into red. The measurement of redshift is the greatest tool in the sizing and shaping of the cosmos. It suggests that the distance to the farthest reaches of the universe is 15 billion light years. Mapping the heavens in the early 1960s, astronomers identified points of intense radio noise. Through optical telescopes, the sources appear as ordinary stars, but they can't be, for redshift puts them at billions of light years distant. They're not radio galaxies. This one, Centaurus A, is noisy but less energetic. Nor are they Cepheid galaxies, radio sources that have brilliant cores. Cepheids are 100 times less energetic than radio galaxies and at least 10,000 times less than the new sources. But all three are fueled by supermassive black holes, voracious concentrations of gravity. The black holes in the new sources are gigantic, devouring the equivalent of up to 600 Earths a minute. For those radio astronomers have discovered quasars. Quasars are superluminous. They're the most energetic objects in the universe and among the oldest and the most distant, with enormous redshifts. Our sizing and shaping of the cosmos yields yet another great discovery: colliding galaxies. This is such a merger, the antennae galaxies. Simulated on computer, the two spirals don't really collide, but swing through each other like cosmic pendulums. Their gravitational interaction ejects two great tails, like the antennae of an insect. The merger triggers a starburst. New stars are born. The antennae are 63 million light years away. At their center, a firestorm of star birth. This collision is like a spanner in the works. The intruder galaxy has passed right through the larger one, disrupting its structure. Here's a real picture of the same effect. It's the Cartwheel galaxy, scrambled as one of the small galaxies on the right ploughed through. In this collision, neither galaxy emerges. Instead, a supergalaxy is formed. In 10 billion years' time, that's possibly the fate of our own galaxy. We collide with Andromeda. We live in a mystery. It's called the universe. We can measure it, analyze it, observe it, even explore it. But what is the universe? How did it begin? Why did it begin? And how might it end? Some people reject the idea that it started with a Big Bang. Cosmologists generally accept the theory, but while they can explain how, they have no idea why. This is the theory of the Big Bang. From a single cataclysmic explosion, everything springs. From a speck smaller than an atom emerge matter, space, and time. It's blindingly hot. In the first microsecond, the universe expands to the size of a galaxy. It's a particle soup, growing bigger and bigger. It's so hot, energy spontaneously generates matter and antimatter. They annihilate each other and start again. Matter wins by 1 part in a billion. Matter is to dominate our universe. Protons, neutrons, electrons. The universe is now 1 second old. It's opaque, we can't see a thing. But physicists work it out. This expanding maelstrom seethes with subatomic particles. Atoms are about to form. At 3 minutes from the Big Bang, they create the first chemical elements, hydrogen, helium, and a trace of lithium. For 300,000 years, the cosmos is a fog. But as it expands, temperatures drop, our universe becomes transparent. For the first time, light and other radiation speed across space. A telescope can't show us the early universe. A particle accelerator can. This is an atom smasher. Electrified particles are crashed into each other at approaching the speed of light. For a split second, we're in the earliest universe. The collisions reproduce fleetingly the subatomic particles that abounded immediately after the Big Bang. The veil is lifting on the opaque universe. In 1965, Americans Robert Wilson and Arno Panzaius detect the first radiation of the visible universe. The horn behind them picks up a microwave hiss from every direction, an echo of the Big Bang at minus 270 degrees Celsius. As the universe has cooled, that signal, originally in ultraviolet, has shifted to microwave. It's called cosmic background radiation. This is COBE, the Cosmic Background Explorer. It makes sense of the microwave hiss. Like a super-sensitive thermometer, COBE takes the temperature of the universe, first removing the solar system. Then the Milky Way. What's left is an ancient temperature chart. From the first radiation of the visible universe, evidence that a primitive structure has emerged. That structure takes 1 billion years to develop. Ever expanding, galaxies in clusters, clusters on strands, the voids between growing wider and wider. Here, mutual gravitational attraction draws groups of galaxies into clusters, and clusters into superclusters. How galaxies form is a puzzle. We know how a supercluster like this evolves, but its collisions and mergers make it hard to unravel the earlier history of individual galaxies. Computer simulation confirms that the evolution of a supercluster is a violent affair. Some galaxies spin right out of the system. Gravity conducts a chaotic dance. It may last for billions of years. Young galaxies in the very early universe appear small and irregular, the product possibly of the repeated merger of smaller clumps. Those infant galaxies bear little resemblance to a mature spiral like this. Current thinking is that galaxies grow from smaller aggregations of matter in merger after merger. Subsequent development like this is better understood. Galactic interaction is the norm. Often it's cannibalism, big galaxies ingesting smaller ones. It continues to the present day. But what is the present day? How old is the universe? If it's expanding relatively slowly, we can deduce that the Big Bang happened some 15 billion years ago. If it's expanding rapidly, then the universe is younger, between 10 and 13 billion years old. Winding back to the Big Bang is one way. Another method of aging the universe is to look at stars hovering outside the plane of our galaxy. Such stars form groups of up to 1 million. Called globular clusters, they contain the most ancient stars in the universe. By analyzing their light, the age of these stars is initially set at up to 15 billion years, but the first windback results put the age of the universe at only 11 billion. These stars can't be older than the universe. The satellite Hipparcos helps resolve the issue. Its mission is to measure the distance of thousands of stars with unprecedented accuracy. Hipparcos employs parallax. It measures the shift of a foreground star against a more distant star. It does so from opposite positions in Earth's orbit of the Sun. The accuracy of Hipparcos is like measuring a golf ball on the Empire State Building from the other side of the world. Hipparcos proves that certain stars are 10% farther away than we thought, making the universe between 13 and 15 billion years old. Hipparcos finds that globular clusters are also farther away, making their stars younger, at between 12 and 13 billion years old. The older the universe, the slower it expands. So could it stop and reverse? Maybe, but one theory suggests the expansion of the universe will go on, till, like a firework, momentum runs out. The universe will be dispersed, bleak and lonely. The theory of the Big Crunch is more dramatic. When expansion is exhausted, the universe teeters and reverses. It could only happen if there's enough matter in the universe. Matter creates gravity. Only gravity can orchestrate such a terminal crunch. There may be enough matter, for 90% of the universe is thought to be invisible. No one has ever seen a black hole, for nothing, not even light, escapes such gravity. Like black holes, 90% of the universe is invisible. Astronomers call it dark matter. This hidden mass is undetectable at any wavelength from gamma rays to radio. With 9/10 of the picture obscured, our ideas of the universe could be quite wrong. Dark matter may be largely responsible for the development and structure of the universe. The problem is, most of that structure is invisible. For all we know, the cosmos is made of monsters. Two stars orbit a common center of mass. They have a mutual gravitational attraction. We don't see the gravity, but we see its effects. The gravity of dark matter affects the rotation of this galaxy. Its spin is measured by the colors of the Doppler effect. Results show that outer parts of the galaxy spin much faster than its visible matter justifies. The cause is dark matter. Probably a hidden halo of up to 10 times the visible mass accelerates the galaxy. But dark matter shouldn't be confused with the dark clouds that pepper this galaxy. They're just visible dust. The matter we seek tugs invisibly on these stars. And it hints at a presence in these clusters of galaxies. Their interactions suggest up to 100 times more matter than we see. But what is dark matter? Is it dead stars, or failed stars, or black holes? Or is it exotic subatomic particles? This is the visible cosmos as we know it. The nature of dark matter and its part in shaping our universe remain two of the greatest mysteries in cosmology. A superstar draws matter from its smaller partner. The big star dies in a supernova, but the partner survives, still orbiting, still losing matter. For the superstar is now a black hole. In the real cosmos, we'd see the surviving star apparently orbiting an empty space. It's a clue used by astronomers to detect black holes. This is another. Although invisible itself, a black hole distorts light and space at its rim. Approach too close, and you're spaghettified. A black hole is a collapsed star of such density, such gravity, that from within the rim, nothing escapes. To form a black hole, the core of the exploded star must be at least 3 times the mass of the Sun. But imagine Earth as a black hole. The mass of our planet is compressed to just 8 millimeters. It is so dense that light cannot escape, and nothing travels faster than light. But light can be bent, and it helps us find dark matter. Here, light from a distant quasar travels to Earth. Put a big object in the way and our picture distorts. The object might be a galaxy with lots of dark matter and enormous gravitational pull. That gravity creates a crazy lens. It tugs on the light of the quasar, bending and multiplying its image. The picture we get on Earth is 4 images of the quasar with the lensing galaxy at the center. The degree of light bending reveals the amount of dark matter in the galaxy. When the lensing object is less symmetrical, it smears light. The blue arcs are far-off galaxies distorted by the cluster in the foreground. But the principle is the same. Gravitational lensing enables scientists to weigh dark matter. In the Milky Way, shrouded by the stars that crowd our galactic center, is a ring of gas. It has the mass of 30,000 suns. To many astronomers, such a swirl is evidence of only one thing, the pull of a massive black hole, a throat at our galactic center that has swallowed 1 million suns. Galactic collision is thought to spawn supermassive black holes. Like celestial dancers, two galaxies merge. A supermassive black hole is formed when the galactic cores unite. This is Centaurus A, the marriage of two galaxies, a white one shaped like a basketball and the dark one that we see edge on. At their single heart is a supermassive black hole. It has 1,000 times the mass of that hole in the Milky Way. And here's another, just as big. A supermassive black hole is surrounded by an accretion disk. Subject to irresistible gravity, matter swirls inward. Some matter jets at right angles to the disk, saved at the brink by the shock wave around the central vortex. Every hour, the equivalent of 4 Earths is consumed. This is an even bigger supermassive, a hole with the mass of 2.5 billion suns. It's at the center of the galaxy Virgo A. A great plume of material ejects across space. Here is Virgo A from the Hubble Space Telescope, the jet plainly visible. And this from a telescope on Earth. But the most incredible black holes are linked to quasars. Quasars burn at the center of remote galaxies, so fierce and bright that they outshine the galaxies themselves. Quasars are fueled by the hungriest black holes, supermassives that consume the equivalent of 600 Earths an hour. These are Hubble pictures. Quasars are among the most luminous and powerful objects in the universe. Albert Einstein, the great 20th century physicist, predicted many of the effects of supermassive objects. His general theory of relativity explains how bodies not only bend light, but distort the space around them. Our universe ripples with the push and pull of gravity, the exertions of supermassive objects. A black hole is the ultimate distorter. It so bends space and light that we've no idea what happens inside. It could be a wormhole to other parts of the cosmos, even to another universe.